So only 40% of students actually got this question right, and this was actually the very first question on the June 2023 paper. So hopefully you guys can do a little bit better. We're going to be going through the first few questions of that 2023 paper and going through a few of the common mistakes and pitfalls that students do and what you would basically repeat if you want to fail your chemistry paper 1 exam. So let's go through it with this question first. Atoms were originally thought to be tiny spheres that could not be divided. So this is basically drawing on your knowledge of the atomic model and how it basically developed. The plum pudding model of the atom was then developed. Figure 1 represents the plum pudding model of the atom. And for 2 marks, then the question is, describe the plum pudding model of the atom. So it's 2 marks, you want to give 2 points, and you want to give the 2 key points of the plum pudding model. So what would you guys write for 2 marks? I'll give you a second. So for 2 marks, you basically should write that you have a ball of positive charge. And you can see it's basically depicted for you in the diagram that you have a ball of positive charge and you have negative electrons embedded within it, okay? That would be enough for the 2 marks. So it seems quite simple, but surprisingly, just 40% of students actually got both of these marks. So what were some of the common pitfalls then in this question? Well, some students, instead of saying charge over here, they actually said energy. So charge and energy are 2 different things, and you wouldn't get away with it if you said it was a ball of positive energy. It's not a ball of positive energy, it's a ball of positive charge. So you do need to remember that one. Some other students also did name the electrons. Some people got it confused by saying that the electrons are basically outside of this ball of positive charge. Remember, in the plum pudding model, these electrons, you can see in the diagram, they're actually embedded within the ball itself. And that's why it's like a bit of a plum pudding. Some students maybe get it confused with the nuclear model that was developed later. And so overall, what is this question testing then? It's testing your knowledge of the development of the atomic model. So at a high level, what things do you need to be familiar with? Well, in terms of the atomic model, the first thing is you had these small and indivisible atoms. So that was basically what they said in the first place. Then it developed into the plum pudding model, which is over here. What happened after that is you had the alpha scattering experiment, and that basically led to the development of the nuclear model. And so they could also ask you about that. And since a lot of students struggled with this question, they might in the next future papers ask you about this. And the last thing then that you can also add here is that you then had James Chadwick come along, and this fellow, he actually discovered the neutron. Well, he provided the experimental evidence for the neutron anyway. Okay, so that's how we got to our modern day nuclear model with the protons and the neutrons in the nucleus and the electrons orbiting around on the outside. Okay, the next question we're going to be looking at is 1.4. So it's basically the same question, just the 4th part. And later on, basically, they're asking you about this element tennessine. Okay, so you can underline it there. Tennessine was first identified by a small group of scientists in 2010. It's just one reason why tennessine was not accepted as a new element by other scientists until 2015. Okay, so eventually it was accepted, but initially it wasn't. Okay, now this is a 1 marker. So 1 markers, you're thinking they should be quite simple, should be quite easy. Now, actually, some of the 1 markers can be some of the hardest questions that you're going to get in your paper. Now, in this case, basically, they're asking you why, when something is discovered in the first place, you made the scientific discovery, why would that not be accepted straight away? Why did it take 5 years for it to be accepted? So go ahead, what would you guys write for this one? So the answer is basically that you need time for peer review. Okay, so this is the key concept that they're testing you on, is when you make new scientific experiments, when you make new scientific discoveries by doing scientific experiments, what actually happens? What is the process for that to become accepted as a scientific fact? Okay, so there is this process of peer review, and this is in your specification. Okay, so in the AQA specification, it's there as well, and in all the other specifications, they will have something similar. And the idea is that you need to be able to explain and recognize specifically the importance of peer review of results and of communicating results to a range of audiences. So the idea is, if this one group of scientists, this one group of scientists is a small group, then they discovered this element, why would we not just take their word for it? Well, anyone could go anywhere and say that they've discovered this and they've done this experiment. The whole point is that we want reproducible studies that other people can go and verify that they've actually discovered what they say they've discovered. Okay, so this whole point is that we need peer review, and there's going to be some time period for that. So it's kind of a common sense one, but it is one that students still struggle with. A lot of people did say it's to do with the scarcity, okay, that tennessine is not that common. Now the problem with that is, well, tennessine isn't that common, but this small group of scientists managed to discover it, so why would that not affect them? And it would affect the later scientists. It doesn't really make sense. And once you've discovered it, surely scientists can share that around as well. So it's not really a relevant point. Okay, so it's very similar to the previous question. It's all to do with scientific thinking, and actually just 20% of students actually got this one right. So you do remember about peer review in your exams. It's a key experimental point. Okay, the next question we're going to look at again is an experimental question. So we're told that the student basically repeats some experiment 3 times, and they can see, well, more than 3 times, 3 more times. You can see they actually do a total of 4 times, and you get a mean over here. And the table shows the results of 8 grams of ammonium nitrate. So for this question, we don't actually need to worry about what the actual experiment was. We're just going to focus on the results part. So the question is asking us, the student recorded the mean lowest temperature of the solution for 8 grams of ammonium nitrate at 60.5 plus minus 0.3 degrees. Okay, it's basically just this measurement, right? So they said the mean of their measurements was 60.5, and they've added this plus minus 0.3 degrees Celsius, and that is what the question is zeroing in on. Okay, do we understand what that plus minus means? So explain why the student included plus minus 0.3 degrees Celsius after the mean lowest temperature. Okay, so I'll give you a second just to write down what you think. Remember, it's 2 marks. So what would you write for 2 marks? Well, the first mark is relatively simple. So if you guys understand what that plus minus 3 is, that would be enough to even get you the first mark. You just have to say this is an uncertainty. Okay, and in particular, this is an uncertainty, but you want to say what is it an uncertainty about. Okay, so this is not the uncertainty in the measurements. So each of these individual measurements will have some kind of uncertainty. Every time you take a measurement, there will be some kind of uncertainty in there, but that depends on how you've actually measured whatever you've measured. Now here, we're giving an uncertainty of the mean, okay? So after the mean value, we're given an uncertainty. So this is the uncertainty in the mean value, okay? Now the next question is, and what you need to say for the next mark is basically, how did we get to that? How do we know this is 0.3 degrees Celsius? Why is that the uncertainty in the mean? Okay, and very simply, all it is the mean value was 16.5, and if you do 16.5 minus the top value, which was 16.8, what do you get? Well, you get 0.3. Or in fact, actually, it should have been the other way around. So we should actually swap these. So you do the top value minus 16.5, which was your mean, and that gives you 0.3. And then you do basically a very similar thing. You do your mean minus the smallest value, 16.2, and you get 0.3. So you can see in this case, right, the range is clearly 0.3. You can go 0.3 up, you can go 0.3 down. So it's plus minus 0.3 is going to be your uncertainty, since that is the range of your results, very simply, right? Now, a really common misconception with this one is a lot of students, they worked out the range of the results and they divided it by 2. So essentially, you can do that. So if you work out the range here, you would get 16.8 as your top value, 16.2 as your smallest value. So the range would be equal to 0.6, and then you would do 0.6 divided by 2, and that would give you 0.3. So this is actually not the correct way to do it, okay? When we're looking at the uncertainty of the mean, we need to take the range from the mean value, okay? 16.5. So the median value, in this case, it's the same thing, gives you the same answer, right? But the median and the mean might not be the same, and this is what you're doing. Basically here, you work out the uncertainty about the median, which is not what you're trying to do. Okay, so in fact, and if we look at the kind of answers that the students gave, well, actually fewer than half of the students obtained even a single mark here. So I would hope that most students, most of you watching this video, will be able to get this one. Sorry, not this one, but actually this one, to say that it's just an uncertainty of the mean itself. That is just a fact that you need to understand. The second point then, in terms of working out that the 0.3 is just the range from 16.5 plus 0.3 gives you the top value, and minus 1.3 gives you the bottom value, okay? If you give either of these calculations, you'd get the second mark. Okay, and the last question that we'll do for today then is another experimental question. So it's basically actually the next part of that question. And again, it's only 1 mark. So you're seeing a theme here. These are not worth loads and loads of marks. They're normally 1 or 2 markers, but they're based about experimental understanding, okay? So don't forget to revise that, okay? You can revise all your normal topics, but also make sure you're revising how to do experiments and how to process and analyze experimental results. So the question here we've got is, which type of error is shown in table 3? So table 3 we saw before. It's this table over here, and it's asking what kind of error can we see over here. So I'll just clean it up, give you guys a good view, and just looking at this, what do you think the error is? It is multiple choice actually, so it should even be a little bit simpler. It's either random error, systematic error, or zero error. And so we can see here from the table, this can't be zero error. Okay, the reason why it can't be zero error, we're not given any measurement which we know should be zero. Okay, if trial 1 for some reason we knew was meant to be 0 degrees Celsius and actually 16.2, then we can clearly see there's a zero error here. And a zero error is another type of systematic error basically. But is it going to be any other kind of systematic error? Well, let's look at it. Well, here now you're deciding between, is it systematic error or is it a random error? Now, if you look at the results themselves, 16.2, 16.6, 16.8, 16.4, that is quite random in terms of the way that's spread out. You can't really see a pattern there. There's no indication that there's something going wrong at the systematic level to make all of these 0.2 higher or 0.2 smaller or something like that. There's nothing like that. There is no pattern here that you can see. And therefore, your only option really is to say, look, this is just random error. Okay, so it's only 1 mark and it's fairly only half of the students actually gave the correct answer. And one of the more popular answers was actually systematic error. A lot of students say systematic error. There's nothing actually in the questions to suggest that it's systematic. Okay, so we'll leave that there. You can see we just did a few of the questions. If you find these kind of videos useful, do let me know. Put it in the comments below. And good luck with your paper 1. And I'll see you in the next one.